Okay, so in this video, I'm going to talk about bootstrapping and show the implementation of bootstrapping that we did in the previous video, particularly using the coefficient of variation example. So recall that the issue or the process or sorry, the system of the data was that x1, x2, etc. Our data xn is from a normal distribution with mean mu and variance sigma squared, right? And our interest is in we want to estimate theta, which is equal to sigma divided by mu. This is called the coefficient of variation. And our issue was that we have an estimate of that. We can just replace the sigma by the sample standard deviation and mu by the sample mean. But the challenge is to understand the quality of estimation of this parameter of this estimator is difficult. And in this case, we can use non-parametric bootstrap or parametric bootstrap, both. And so I wanted to show you code for that. So first, I'm going to simulate data sets just so I have some control over what's going on. So my mu is 5 and sigma squared is 2. And the number of data points I'm going to draw from my target normal distribution, which is what the data assumes, is our norm n. It's going to be 100 observations right now. We'll change that in a little while. And for this, if I just say, so if I just do square root of sig2 divided by mu, this is my true coefficient of variation. And this value is 0.28. Okay, so that's my true coefficient of variation. I'm going to fix some parameters in order to make my final confidence interval at the end. I need an alpha value, so that I'm fixing at 0.05. The n's for the quantiles are going to be alpha by 2 and 1 minus alpha by 2. So I'm going to call this n's. The number of bootstrap samples. So this is the number of bootstrap samples. And I'm going to fix that at 1,000. Now, the first thing I do, up until now, I'm doing housekeeping. I'm generating data, then I'm setting up my system. Now I actually assume I don't have the actual access to the truth. And I'm using the data to actually estimate the various parameters without knowing what the actual underlying truth is. So theta hat estimate of the coefficient of variation is then the standard deviation, sample standard deviation SD hat, divided by the sample mean of data, and that is theta dot hat. So what is the estimate of theta dot hat? That is 0.298, and look, that looks very similar to 0.28, so we're pretty good, right? I should, just so we can all replicate this nicely, I should set seed. So let me just set seed at 1 and do this one more time to get what theta dot hat is, and that is 0.246. So not so good with this particular data set. So we are already seeing that this may have large variability. Now, if we don't want to assess variability, we can be done. We have calculated theta and we're good to go, right? An estimate of theta. But we want to assess variability, so we can do non-parametric bootstrap. To do non-parametric bootstrap, I create a vector np.boot, and this is going to store my theta stars. Okay. For each value, small b in 1 through capital B, in foo, I do sample indices 1 through n of size n, but sample them with replacement. Okay. That is the indices of the resampled data points. And then my bootstrap sample is going to be the data set dat sampled and subsetted only at those particular indices. Okay. And then np.boot at the bth index over here is going to be the SD of this bootstrap sample divided by the mean of the bootstrap samples, right? So these are the theta stars. Okay, I can run this, and that's going to complete my non-parametric bootstrap. Now we'll look at the results in just a second, but before that, I'm going to implement parametric bootstrap. And now in parametric bootstrap, what I want to do is take my parameter values and put them in the known parametric distribution of my data. I don't know what the parameters in the distribution are, but I know that it's in the Gaussian family, right? It is a Gaussian distribution. So for each bootstrap sample, I go and I draw a new R norm sample of the same size n, with the mean being equal to the mean of the data and the standard deviation being equal to the standard deviation of data, because these are the two quantities that I'm actually utilizing in my theta dot hat. Once this bootstrap sample is available, then I just do SD of the dot sam divided by mean of the boot dot sam, and that is stored in parametric bootstrap. And I can run that. Fab. Now I can do my confidence intervals. Okay. So my confidence intervals for non-parametric bootstrap for my actual parameter theta, which is the true coefficient of variation, is 0.21 to 0.2811. So that my actual value is over here, and that is looks like my non-parametric bootstrap in this instance does not contain, it gives us a random interval that actually does not contain my true parameter in this case, which is possible because only a few percentage of time will it actually do it. And my parametric bootstrap in this case also doesn't contain, which is okay, which is perfectly fine, because we don't expect the parametric and non-parametric bootstrap to give us an exact answer of what's going on and be able to pick everything up exactly, but it does give us a measure of the variability in general. So for example, we can look at how big these intervals are and assess that, okay, things are quite, this is quite a big confidence interval. And we can also plot sampling distributions, or I should say plot estimated sampling distributions for GN, right? And the way I can do it is I can take all my np.bootstrap samples and just do a plot on it, right? A plot of the density on it. So it calculates the approximate density from all the theta stars that it's obtained. And so this blue curve that you're seeing is our guess for GN. And similarly, the red curve is going to be our parametric bootstrap guess for GN. And they look very similar to each other, okay? Right? And you can see that the way they're structured, one quantile will be here and another quantile will be here. Right? So this is how the non-parametric and parametric bootstrap give us an understanding of the distribution of the estimator. Now we can do the following, is I can change the original data from 100 observations to 10 observations, in which case you can see that in the previous plot, my sort of distribution was from 0.18 to 0.32, and now it's going from 0.05 to 0.3 or even further. So I've actually increased my variability of my estimator, because so what this is saying that the sampling distribution has larger variability because now the data size has decreased. So if I have less data, my estimator is not as robust and not as believable, right? In this particular case, parametric bootstrap is much better because see, it has that the actual truth within its interval, and it is potentially more accurately able to represent the sampling distribution, right? I can now go back and change the size of the data set to 1,000. And so think about it for a second. As to once I've changed the size of the original data set to 1,000, how do we expect the densities of the sampling, the density of GN, the density of theta hat to look like? And if I run this, I know that if I've increased with the size of my data, then the quality of estimation of theta has improved, which means my estimated theta hat should have lower variability. So it should be a much tighter sampling distribution. So, right now I'm going from 0.05 to 0.35 looks like. And when I run this, it's going to take a little bit time. But now I go from 0.27 to 0.32, and my intervals now have the truth in them as well. So the quality of my intervals definitely improves in this particular case when the data size is 1,000. So when the data size is very small, this can be quite, Bootstrap can be unstable because see, there's not a lot of options. I don't have that much data to resample from, right? But when the data size is fairly large, things can actually work fairly well and we can get a good understanding of the approximate sampling distribution. Okay, so I would like you to encourage you to go back and think about how would you generate and visualize the sampling distribution for the sample median of the gamma random variable, and see whether you can write code to be able to do that.